Here's another useful coordinate system. It's called spherical coordinates. We do live on a sphere after all. Um, so let's start off in a regular XYZ coordinate system. What I want to do now is I want to take a point in space here. Now it's kind of hard to tell where that is, but if I drop a perpendicular down here, it doesn't look very perpendicular. If I drop a perpendicular down here to the XY plane, you get a better sense of where that actually is. So I want now to use, like in polar and cylindrical coordinates, this angle was theta here, measured from the positive x-axis. But now, rather than measuring r horizontally, I want to measure r as a radius from the origin out to the point that we're talking about. This is called rho, Greek letter rho. And then from the z-axis down here, this angle is called phi. Okay. Now, this is a lot like longitude and latitude. Longitude is definitely this angle theta. If you think about on the Earth, you have your longitude lines going this way and the latitude lines going this way. Those are angles measured from the center of the Earth. The difference being is that latitude is measured with 0 at the equator and going up from there, where we're measuring 0 from the North Pole essentially and going down. So very closely related to longitude and latitude, but not exactly. In order to make the conversion between x, y, z and rho, theta, phi, and that's generally that's the order we will use them on different books to different orders, but generally we'll do rho, theta, phi. Okay. I want to convert it. Well, I've got a picture here that's going to help me out. In particular, let me draw sort of another line in here that's parallel to this one. So parallel to the XY plane here, let me connect that back to the z-axis. Okay. So that's a right angle right there. Not that I made it look like a right angle. It looks better. Now, I think I can see clearly what the z-coordinate is then, because I've got a right triangle here with an angle of phi and a hypotenuse of rho. So the z-coordinate here looks like the z-coordinate, so this x, y, z, looks like the z-coordinate is rho times the cosine of phi. Not rho times cosine of rho, rho times the cosine of phi. There we go. Now I'm going to see if I can get the x and y coordinates, and I see the x and y coordinates down here, x and y. So what I need to know is what this length is. This is what we were calling r before. Well, r is equal to, r is the same as that here, so it looks like rho sine phi. Actually, for cylindrical to spherical coordinates, there's your conversion. You got z, you got r, and theta is the same thing. But I want to go to x's and y's. So now I know what r is. X is equal to r times the cosine of theta. So it's rho sine phi times the cosine of theta. And the y coordinate is r times the sine of theta. So the y coordinate is rho sine phi times the sine of theta. Okay. So those are the conversions. If you know rho, phi, and theta, you can calculate x, y, and z. If you want to go the other way, how would we do that? First of all, I think we can see that rho is equal to Well, the square root of x squared plus y squared plus z squared. It's the distance from the origin, right? We still have the relationship that, actually, I don't want to write this way now that I think about it. I'm going to write it this way because, like polar coordinates, we can allow rho to be positive or negative. Theta and phi essentially tell you what direction to look in, and then rho is positive if you move in that direction, or negative if you move in exactly the opposite direction. So I'm going to leave this way. Likewise, that the tangent of theta is still y over x. To calculate phi, directly from x, y, and z, I'm going to say it's the inverse tangent of r over z. So the tangent of phi is r over z, which is the square root of x squared plus y squared over z. Okay. We may have to be a little careful with the plus or minus sign on that, but anyway, there's conversions between spherical and rectangular, or rectangular and spherical. One direction is nice, one direction is not so nice. The thing is, just like polar coordinates, any point in space has multiple representations in spherical coordinates, right? As long as you take anything coterminal with theta here, you're going to end up with the same spot. Now, it's not quite so simple as saying, well, if you have sort of, if theta is off by pi here, so if you're sticking out in this direction, you can't just say take rho negative, because with the same phi, so if I've got a situation here where I have one theta sticking out this way and one theta sticking out that way, with the same phi, so the same angle down here or the same angle down there, right? Those are very different spots, and just taking rho negative doesn't get you in the right place. But there are ways to end up with, if somehow we can be looking down this way. Yeah, anyway, but we can get multiple representations. Some basic graphs that we might want to look at. Just rho equals a constant. Right? If you have rho equals a constant, then you're saying I want all the points where the distance from the origin is constant. I don't care what the two angles, I don't care what theta or phi are. So what you're talking now is a sphere of radius c. Any point on that sphere has the same rho value, and theta and phi are arbitrary. How about if I have theta equals a constant? Actually, I guess that's phi equals a constant. Well, I meant to say theta, but I wrote a phi. So let's say phi equals a constant says that you have a certain distance down, or sorry, a certain angle down here, and then you don't care what theta is, so you can rotate that around, and you don't care what rho is, so you can go out as far as you want in any direction, in whatever direction you have, you can go out as far as you want. And rho could also be negative, so it looks to me like phi equals a constant is describing a cone. Now, how about theta? Let me try this again. Theta equals a constant. Theta equals a constant. So we've got some fixed angle here. And then you can take phi to be anything you want. So that is describing, like that. And these are different values of r, or sort of rho, a little distance away. So I guess, yeah, it looks like what we're describing here is that plane through the origin containing the z-axis here, just like in and cylindrical coordinates. Okay, so this is that constant angle C. Right? So anyway, there's those. You start getting any more complicated, and the graphs start looking really interesting. It's quite common that when we do spherical coordinates, they do rho as a function of phi and theta. So you have like rho equals, well, what if we have rho equals theta? If you have rho equals theta, so as theta gets bigger, you have to be further away. But then phi can be anything you want. Wow. Wow, what does that look like? So here's my online graphic calculator, the 3D version. And I want to look at rho equals, what did I say, theta? So let's do a theta here. In live math, if you type a single quote and then a letter, it gives you a similar Greek letter. Apparently, use t in place of theta. Okay, sorry. And p in place of phi. Okay, so t in place of theta. All right, there we go. What the heck is this? Oh, this is interesting. See, what we have here is, how to best describe this? You see that circle right there? That's for theta equals 2 pi. So, sorry, yes, theta equals 2 pi. So rho is 2 pi throughout that whole circle. Phi is changing, which is why you've got this vertical circle. Now, really, I should be drawing the whole circle, but I'm only drawing half the circle. Apparently, when I'm plotting this curve, this is the blue one, I'm only going from 0 to pi on the phi. If I went all the way around, 0 to 2 pi, I think it might get a little trickier to see what's going on. Very, very cool. Let's make that bigger. So what I'm looking at here is circles that, so pick a value of theta. Can I see? It's not going to look any better. Pick a value of theta. So what I'm seeing, the biggest one is 2 pi. So I've turned through an angle of 2 pi, and now I'm forcing rho to be equal to 2 pi, and then phi is anything you want. So that draws that whole circle passing through the z-axis. For different values of theta, so for instance a little bit smaller, you've got these other circles. And so as theta changes and you rotate around, you're getting bigger and bigger circles, and you're drawing this sort of double clamshell. Not clamshell, but snail shell, I guess. So if I just go to 1 pi, that cleans that out a little easier. I'm also plotting only thetas from 0 to, what am I doing? 0 to 2 pi. I could do more or less, depending on what I want. If I do more, this shell should wrap itself around even more. So if I go to 3 pi, yeah, now I'm you see it wraps all the way in there. Unfortunately, that I can't make this semi-transparent, or can I? No, I can't make it. No. Some of the older versions, I used to be able to make the surface sort of semi-transparent so you can see through it. But anyway, there's rho equals theta.